All right, so here, if the exponential growth law applies to the population growth in Nigeria, find the doubling time to the nearest year of the population if it grows at 2.1% per year compounded continuously. Well, what do we know about that? So if we can get our penciled right, we know that P is going to be equal to P0 e to the RT. That's our growth rate. Now, what do we know? If we're doubling our initial population, that means P is going to be 2 times P naught, and our rate is 0.021 times t. Now we just have to solve, and that's p naught. We just have to solve this. So let's cancel stuff. P naught cancels p naught. Now what we can do is we can also take the ln of that side, and we can take the ln of that side. And when we do that, that comes down in front of the ln. Oops. And so now what do we have? We have the ln of 2 equals 0.021 t ln of e. Well, that's just 1 divided by 0.021 divided by 0.021. So t is equal to just the ln of 2 divided by 0.021. And that gives us, to the nearest year, it looks like 33 years. Okay. And so that would be our solution to this one. And again, we know our equation already, population growth, and so we can use that as we go. All right, so let's continue on with, now we're going to turn our attention to radioactive decay. So, a little interesting thing, in 1946, Willard Libby, who received a Nobel Prize in chemistry, found that as long as a plant or animal is alive, radioactive carbon-14 is maintained at a constant level in its tissues. Once the plant or animal is dead, however, the radioactive carbon-14 diminishes by radioactive decay at a rate proportional to the amount present. So in this case, dq dt equals rq. Q of 0 is equal to Q sub 0. Now, this is another example of the exponential growth law, but in this case, we're going to decay. So instead of increasing, we're decaying. So that means R has to be negative. And they found that the rate for R, in this case for radioactive decay of carbon-14, is this value. So this is the value we need to know. And so then with that, we can actually solve problems. Okay, and that's what we're going to do in this next example. So it says a human bone fragment was found at an archaeological site in Africa. And so that was kind of our initial thing. And now we're supposed to estimate the age of the bone to the nearest 100 years if 50% instead of 10% of the original amount of carbon-14 is present. Okay, so, well, what do we know? Well, if we want to follow it all the way down, what we can do is we can say, well, we know that dq over dt equals the r of q, and then we know dq over dt is equal to what? That negative 0.000123 q, if I can write a q. And then if we do all that derivatives, we find that q is equal to what? Q naught, and then e to the negative 0.12312338, and then a t. Okay, so that's really, working our way down, and that's the equation we know already. So we could have started here, or we could have worked our way down and got to that. Now we want to know what? 50% of the original sample. Well, 50% of the original sample, if that's the original sample, this side's going to be the same, but this is going to be half of that original sample. And as we did before, we're going to say, well, that cancels that when you divide both of them by Q naught. We can take the ln of both sides. When we do that, this comes down in front. And so now if we do that, let's put it over here. ln of 0.5 equals a negative 0.12312338, and then times the t, then ln of e, well, that's just 1, divided by negative 0.00012338. Divide that by negative 0.12312338. And so t is equal to, and we plug that into our calculator. And we get t is equal to 5598.9, but they want it to the nearest 100 years. So that's just going to be 5,600 years. So that's how old that sample of bone was at that archaeological site. All right, so let's pause there and we'll come back for some more.